Since last week, not last week, on Tuesday, okay, we was going through solidification. I was not that well, so before, okay, start recording ready, right? All right, it's recording now. Okay, let me share the slideshow. Okay, I will go through again with all of you on solidification. Okay, I'll go through again with all of you on solidification. So whoever who don't understand or still feel not that comfortable with the topic 4, worry less, okay, because I'll be guiding you again on this. Okay, it's very simple and very interesting. Believe me, guys, engineering materials, anything to do with materials and engineering is fascinating. Okay, that what sparks me to become an engineer when I was young, when I was in your age. Okay, engineering is very fascinating, but now when I grow older, my focus is more on environmental engineering. Okay, there's a saying, when you grow older, you'll be getting more wiser. So now my focus is on environmental engineering, where I try to reduce pollution and try to think of how to convert waste material into energy. That is also a fascinating branch of engineering. Okay, you guys are young generations. Usually in my class, I always start off with a small stories on. If you are my student previously, usually in my class, I'll start off with a small story on how to preserve environment and what are the things that we can do as a human to conserve environment, because there's only one place for us to live, which is Earth. Right? Think about it, guys. Okay, solidification. All right. So let's start with solidification. Now, guys, previously I give you a lecture on solidification, where solidification is a process of converting back liquid into solids. Okay, converting back liquid into solids. Now, in order for you to convert liquid into solids, atoms in liquid form possesses high energy content. Okay, you know that, you should know that by now. Solid, low energy; liquid, high energy; gas, highest energy. We are talking in terms of kinetic and potential energies, internal energies, PV. Okay, kinetic and potential energies. So in order for atoms, guys, just imagine, in order for atoms to become back solid, it need to release the energy. It need to go into sleeping state. Okay, that is where this guy comes in. Where is the guy? Over here. The Gibbs free energy. Okay, this is a statement that that explains how does the energy, no, not how, what type of energy is involved in the process of converting liquid into solids. Okay, now back to solidification. Now let's talk about metals. So there are two steps involved in solidification. The first step is nucleation. Nucleation is the formation of stable nuclei in the melt, and the second step is the growth of nucleation, growth of the nuclei into crystals, and then it grows bigger and bigger and bigger until it forms grain structure having a grain boundary. Okay, you can see here. The next slide, slide 3. This is your system, metal. Upon solidification, nuclei growth from a liquid metal, and once it's cooled off, after it's, remember guys, last week's lesson, critical radius, critical size. So once it is beyond the critical size or critical radius, it begins to form crystals. Okay, then automatically when the temperature getting lower and lower, this crystal grows into bigger size, where you have overcome the surface energy, and it grows into grains, and you have a boundary layers. That's about it. Okay, that's about topic 4 actually. If you want to look into the helicopter view, okay, bird's eye view, topic 4 is all about this. That's all. Okay, are you clear with this? You know the concept, then we move on. Okay, are you clear, guys? Can you hear me? Okay, all right, good. All right, now, so when I talk about energy, right, you need to release, sorry, the atoms need to release energy. The energy involved is this Gibbs free energy system. Okay, the stability of a system is determined by Gibbs free energy. All right, and Gibbs free energy is governed by the enthalpy. Can. Lua Wen Zheng. Okay, I will explain to you in detail. Don't worry, I'm healthy now. Okay. So the Gibbs free energy system is governed by the enthalpy and the Ts, which is your absolute temperature, and also the entropy. All right, so this is the governing bodies. Now, when you look at enthalpy, enthalpy is the measure of the heat content of a system, and enthalpy is comprises of internal energy and also PV, which is pressure and volume. All right, so your internal energy is the total kinetic energy and potential energy, and this transformation will occur when the heat is being absorbed or evolved. It depends on the changes in internal energy and changes in pressure and volume. So that is enthalpy, okay? Enthalpy. And entropy is nothing but randomness of a system. It's a properties. Unused energy, we can call it as unused energy. Okay, condensed phase. Condensed phase means either liquid or solids. Okay, if you look at the terms of condensed phase is a term used whereby an atom cannot be compressed. Liquid, you can't compress, right? Solid, you can't compress. Gas, yes, you can compress. So condensed phase compromise of what do you call that? Solid and liquids. And in solid and liquids, your pressure and volumes terms are small in comparison to E. Okay, in comparison to E, your internal energy. All right, and then at constant temperature and pressure, a closed system, okay, will be in stable equilibrium if heat has the lowest G. Okay, the lower the G, the more stable the system. So you want to have low energy. Okay, stable system is in solid state. Okay, I repeat, stable system is in solid state. So in order for you to have a solid state, you need to have a very low energy in your system. You need to have a higher stability in the system. If you want to have a higher stability in the system, you need to have lower Gibbs free energy with this G. Okay, let's look at this Gibbs free energy. Over here, comprise of solids. Configuration A has the lowest free energy, as therefore the arrangement when the system is at stable equilibrium. Okay, configuration B here is in metastable equilibrium. Okay, it means that this can be in liquid form. Okay, even though it is stable at the lower state. That is the reason why here. Okay, this is what depicts these graphs. Okay, if you look at Gibbs free energy, the state with highest stability, okay, the state with highest stability is the best compromise between low enthalpy and high entropy. Okay, now if you look at low temperature, okay, solid is more stable, right? So it means that you have a very low E and H, internal energy and enthalpy over here. Okay. If you look at metastable system, which is in solid, high temperature, TS is being dominated. Okay, phases with more freedom of atom and movement. Okay, your entropy is higher, and of course temperature is also higher, so this is more stable. So that is the reason why the statement says that best compromise between low enthalpy and high entropy. Okay, in solid, low entropy, stable. In liquid, high entropy, stable. In liquid, high entropy, stable. In solid, low enthalpy, stable. Okay. So that's on the energy side. Now, the main mechanism of nucleation of solid particles, there are two types. All right, I mentioned to you, one is homogeneous and another one is heterogeneous. Homogeneous and heterogeneous. And I remember I lectured you that heterogeneous is more practical. That's what being used in industry for heat treatment. And homogeneous is very rare because it needs a significant undercooling, whereby heterogeneous you use by the catalyst. Okay, solidification agent. All right, now let's talk about homogeneous. Homogeneous nucleation happens when the metal itself provides atom to form nuclei. So you might pose me a question, how does the metal itself provide atom to form a nuclei? That happens when a material is severely undercooled, the atom movement is lower, right? You are the temperature gradient is huge, you are supercooling it, okay, undercooling, severely undercooling it to very low temperature, and the atom tend to move slower and come close together. So when two atoms comes close together, they bond each other to form nuclei over here. That's the reason why the metal itself provides atom to form nuclei. So what are the driving factors? Is due to the severe undercooling. Please write it down, severe undercooling. Okay. Now, still in homogeneous nucleation, the nucleus stable growth into crystal and it must reach a critical size. Okay, we are talking about critical size. And the atoms below the critical size we call embryo. When the clusters of atom reach the critical size, they grow into crystals. Okay, so this is critical size. Okay, where is it? Okay, let's say this is critical size. Okay, this is critical size. When the atoms comes here, it becomes embryo. Okay, when it doesn't attain sufficient energy, it goes back to liquid state where it'll get dissolved. When the clusters of atom reach critical size and more energy is being fed, which is the GV, and it attains GS, it crosses the critical size and nucleus will form. Once nucleus will form, it will form crystals, and the crystals grows bigger, and then it becomes E green. All right. Now, I was mentioning to you about GV, right? So there's also a student asked me about GV and GS. All right, now let's talk about it. There are two energies involved in homogeneous nucleation. The first one is GV. We call that as the volume or bulk free energy. And the second one is GS. We call that as surface energy. Now guys, listen to me carefully, all right? GV, you can think of, okay, when an atom, okay, when a metal atom, okay, now we are looking into solidifying liquid molten steel. All right, so you have an atom, it is in a liquid state, and it wanted to convert back to solid phase. So in liquid state, you have lots of energy, right? We are talking about atoms now. You have lots of energy. And when an atom intention is to stay put and become solid, it needs to release energy. Am I right? And that energy is what we call as the volume free energy or bulk free energy. Okay, volume free energy or bulk free energy is an energy released by the liquid to solid transformation. So the atom release energy so that it can stay put. Whereas the surface energy, Gs, is the energy required by the atom who release energy to form a new solid surface. Okay, hope that I've given you a clear understanding on this. All right, so energy released by liquid atoms is what we call as volume free energy release, and then the energy required by the released energy atom to form a new solid surface is Gs. That is what I say Gs is the opposing force. It needs to attain Gs. Okay. All right, now, so GV is the driving energy. The driving energy for liquid to solid transformation is the difference between energies of the liquid and that of solid. GV, what drives GV is the difference of energy, difference of bulk free energy or volume free energy between liquid and solid. Okay, so you have two energies, liquid energy and solid energy. The difference between liquid and solid energy, that's the one that drives the atom to go in, become stay put. Okay, the keyword is put, all right? So it is being released, okay, being released by liquid to solid transformation. And the rate of change of GV is the change in free energy per unit volume between liquid and solid, okay? And is the formula for sphere. Solid, liquid solid interface, which is for Gs, and is the area, and the atoms here releases energy to become solid. So the difference between this energy is GV. Okay. Now let's talk about Gs. So once the atom release energy and it stay in one place, it needs to attain some sort of energy to create a solid surface. So that energy is what we call Gs. Energy opposes to the formation of embryo and nucleus. The energy to form the surface of these particles. Energy required to form the surface of the particles. Energy required by the atom. So Gs is simply the energy required to form new solid surface. And you have a new term, gamma, is the specific surface free energy of the particle. So the formula for Gs is specific surface free energy times with the surface area of the particle. Surface area of sphere for pi r square. And Gs is retarding energy, slow movement energy. Okay. All right, now. So now you have GV and Gs, right? So I hope that you understand clearly what is GV and Gs, right? So the total free energy is a summation of GV and Gs, that's all. So GV releases energy, Gs attain energy, the atom releases energy, it attains energy for Gs until it reaches the critical radius or critical size. At some point, it has given much energy to Gs and then it shrinks further, releases energy further from staying put to become freeze. Then it forms nucleus. So after critical radius, it forms crystals and it becomes nucleus. So the atoms stay put, become freeze, and stay at the same place, just vibrating. That's all. If the energy doesn't sufficient enough, Gs is more predominant, it goes back to liquid state again. Okay, so nucleus above critical radius, low energy, energy lowered by growing into crystal. Okay, low energy. Okay, it gives energy more. Below the critical energy, energy lowered by redissolving. Okay, you give energy again for redissolving and then gain energy from high temperature liquid state, give back the energy again. So that is critical radius. Okay, so the determining factor is your critical radius. So your critical radius is the critical G, critical energy. All right. Now, the magnitude of GV depends on the temperature. Of course, higher the temperature, you have more energy, right? So the magnitude of GV is bigger. Can you see? Lower the temperature, the magnitude of GV is lower because you have less energy on the atom. Let's say you have superheated the water to 150 degrees Celsius. So you have superheated steam. At the and on another samples, you have boiling water which is at 100 degrees Celsius. Which one would you expect to solidify faster into ice? Of course, the one that has lower temperature, right? By logic, that is the reason. Because the energy required for you to form a critical radius is lower for low temperature system. Because the radius is smaller. Here radius is bigger. Can you understand? All of these are logics, guys. All of these are very logics. Okay, when you sit and think about it, you can connect the dot easily. That's engineering, okay? And yeah, critical radius. Greater the degree of undercooling, greater the changes in free volume energy. Okay, if you undercool further, let's say you have two sets of experiment. One set of experiment, you put a room temperature water into freezer. And another set of experiment, you put a room temperature water into a super freezer, which can cools about minus 100 degrees Celsius. The greater the change in volume free energy, GV. Okay, but GS, no, GS does not change significantly with temperature. And the undercooling increases, the critical nucleus size decreases. So the nucleus radius size will be decreased for undercooling furthermore. So it is easily for you to convert to solid. The time taken is easier, faster, because the critical radius have been reduced a lot. Okay, so this is the critical radius formula. Undercooling, amount of undercooling required, change of temperature, and also governed by the latent heat of fusion. Latent heat of fusion is another properties for each materials, all right? And this is just an understanding of what is undercooling. Okay. Now, on heterogeneous nucleation, it is more practical. Okay, it's more practical because it requires a very small undercooling, that's all. Nucleation occurs in a liquid surface of container, and you have lots of insoluble impurities, grain boundaries, dislocation, and other structural material. And there's also a nucleating agent that lowers the critical free energy required to form a stable nucleus. This is in practical situation. Heterogeneous usually happens in a pure substance where you have a severe undercooling. Most of the elements, engineering elements that we have now is all impurities, alloys. So that's why we have nucleating agent. That's why we have heterogeneous nucleation used by industries. And this nuclei will form on the nucleating agent. Over here, nuclei will start forming on the nucleating agent. For example, calcium carbonate for steel, molten steel. In molten steel, you pour more calcium carbonate, it will solidify faster. Okay. The formation of stable nucleus will be lower and the critical size will be smaller. That's the reason why, if you look at heterogeneous critical energy is lower than homogeneous critical energy. Okay, because of impurities, and you have nucleating agent as well. So you are altering the energy by introducing nucleation agent. Whereas for homogeneous nucleation, you are altering the undercooling condition to form a nuclei. Okay. All right. And okay, this one I need to show you okay how the grain boundaries will dissolve. I mean will occur. From crystal boundaries, it becomes grain boundaries. Right? And then types of grains, you have equiax grains, where grains smaller in size grow equally in all direction, form in the sites of high concentration of the nuclei, where you have a lot of nuclei. Example, coal mole wall over here and also at the center. Columnar grains are usually long, thin and long, and it grows in one direction where the direction must be perpendicular to the, sorry, parallel to the temperature gradient from high temperature to low temperature, this direction. All right, guys, can you understand? A quick one, a fast and efficient. Lua Wenzheng, can you understand? Good. Any other questions, guys? All of you clear? Crystal clear? Very good. Okay, I have a very high energy level now. I'm healthy. Okay, guys. Harpinder, are you okay? Okay. Any other guys who want some clarification? I just want to make sure that all of you can understand topic 4. Huh? Then, because next week we'll be going into topic 5. Okay, Theo. The graph slide in 14, 14, 15. Graph in slide 14 and 15 shows small increase in total free energy prior to critical size. Graph in slide 14 and 15 show small increase in the total free energy prior to the critical size. Does it mean the particle need to absorb some energy first to reach the critical size? Then it release it when it begins to grow. Yes, it happens concurrently. It happens concurrently. You need to feed energy to GS at the same time release energy to GV. Until GS is being sustained, you can grow the nucleus. If it is not sustained, go back to gel, which is liquid. Okay. Okay, good. So the surface energy is energy required to form solid surface. Why it is gain energy but not released? Okay, energy. Okay, energy needed for you to do work as well, right? So surface energy is the energy required by the atom to do work to create a new, what they call that, nuclei, which is a solid surface. At the same time, it has tremendous amount of energy that needs to be released for the atom to stay put. So let's say you have 10, okay, let's say you have an energy of in a magnitude of 10. 5 is given to GS, and then another 5 is given to GV. Simply put in that way. So the net energy for the atom is 0. So it becomes solid and stay quiet in a place and it becomes solid. Is it okay? Lim Wen King? Okay, good. All right, guys. So, okay, now for today's lesson, just a continuation of last week's lesson, kinetic of solid state transformation. So now you know that temperature depends on the nucleation growth and transformation rates, right? It depends on the temperature, heat treatment, and also time dependence. We call that as kinetic transformation. How long do you want to heat a material before quenching or before annealing? Okay, that is time dependence. It is an important aspect in heat treatment of material. Okay, logarithm of heating time, you look here, this is nucleation. Okay, this is your, must be somewhere around here is your critical radius. All right, so once it have achieved crystal, it starts to grow. At the mid of your growth, this is just an analogous, is the fraction of transformation before it becomes pure solid. And once it is pure solid, the fraction is 1. Okay, fraction of the reaction that has occurred is measured as a function of time while the temperature is maintained at constant. That's the reason why in an oven you maintain a constant temperature. You put a material inside the oven and you set a timer. The timer depends on the type of material that you are using for heat treatment. Okay, so nucleation. From nucleation to the growth of crystal to become grain, halfway of the growth is fraction 0.5, halfway. And the time is t 0.5. So times 2, you get 1. Pure solid. Okay, and the fraction of transformation can be written in this formula. You can take down the formula. Y is equals to 1 minus exponential bracket minus k Tn, where k and n are time dependent constant for the particular reaction, depends on the alloy. And this expression is referred to as a Rami equation. Okay, you just take note, okay, not a big deal, just a formula. And the rate of a transformation is taken as the reciprocal of time required for the transformation to proceed halfway of completion. Is over here, halfway of completion. This is the rate of transformation, 1 over t 0.5. That is the rate of transformation, 1 divided by the time here, t 0.5. Okay, and then on the last slide, this is just an example. When the time increases, okay, this is your temperature, longer time taken for you to have a perfect crystalline. Percentage crystallization as a function of time and a constant temperature for pure copper. How much crystallization that you wanted to achieve when you're doing heat treatment. Okay, guys. So I think that's about it for solidification. Next week we'll start our new chapter, which is phase transformation. And the following week, next week is week 5, right? Week 5, let me see. Test 1. So I mean test, week 7 is your test. Okay. And for test, the topic that I'll be testing you is until next week's lesson, which is until phase transformation. All right. Okay, guys, any questions? Any questions? Any questions? All right, quiz 1 will be on week 6. It'll be tested by, it will be random. Okay, I will just post any day on week 6. All right, it's just random. Okay, I can't tell you more on that. And for quiz 1 is on the lecture on the day itself. For example, if I'm teaching next week, I'm game over. All right, so the reason why I'm giving quiz is because I want to make sure that all of you can what they call follow with my lesson. That's the only reason I can think of. Okay, so quiz 1 will be tested on the day of the lecture or on the week of the lecture. So it's just a simple quiz. I will be posting that in here in Microsoft Teams, and you just something like the attendance, something like the attendance. You just need to answer, and that's all. Okay. Objective then. Okay, I haven't think of it yet, but don't worry, guys. Okay, you have a very what they call that. I mean, as long as you can follow me, it shouldn't be a problem at all. Don't worry about that. Just a small piece of advice. Let me. Um, in engineering materials, be it any engineering subjects, if you don't understand terms or any subjects related to engineering, the best way is to think in a logical way. You can get the answer because everything is logics. Okay. Quiz one, there's a mark counted. Yeah, there's a mark for it. For quiz one, you have 10%, 5% each for each quiz. Any penalty to the attendance if not doing well? No. But attendance is being monitored by the faculty, not me. I'm okay with anything as long as you attend the class, but it is being monitored by the faculty. So make sure your attendance is more than 80%. Huh? I can't help you on that. SpongeBob is appearing in my class. For quiz one, I haven't set the quiz one and I don't know what topic, but it will be the topic where I'll be discussing with you on that particular week. For example, let's say next week we have quiz one means I'll be testing on that lecture 5 lesson. For test 1, lecture 1 till lecture 5. Next week is lecture 5. For test 1 is lecture 1 to lecture 5. Okay. Yeah. Online quiz. Like Google Form or Microsoft Form. Frankly, I don't know how to use Google Form actually. I need to learn. Okay, I'm very bad in IT savvy. I'm a classical person. Okay, I will upload lecture 5 by weekend. By Sunday, yeah, by Sunday. Saturday or Sunday. Or maybe today, okay? Quiz topic 5, phase diagram only. No, quiz is on week 7. Week 7. And then you have your assignments as well, which will be on week 9. Okay, a simple assignment. Okay, guys, how many of you attended to this class? 52 students. What is the attendance so far? We have 49. We have 52 students in the class, but 49 have signed the attendance. Please sign for the student who haven't do so. Quiz 1 is on week 6. Oh yeah, sorry, my bad. Quiz is week 6. Test is week 7. Sorry, I get confused. Quiz is week 6 and the test is week 7. Yeah, there is only one test. There's only one test. Everything is in the teaching plan. If you refer to teaching plan, I'll be sticking with the teaching plan. Okay. Yes, quiz, 5 marks, 5%. Yo Zing Huan, are you my student for engineering CAT? Yo Zing Huan. Okay. All right, guys. Okay, we have tutorial at 11:30, so I'll be meeting with group P2, right? This is a new tutorial 2. All right. So I'll be meeting group T2 for tutorial later. I think that's all. If you don't have any question, you can leave the Microsoft Teams now. Later, I'll be meeting with tutorial students at 11:30. Okay. Okay. Someone is crying. See you some other times. Thank you very much, guys. Have a good day.